Hi, this is section 4.3, the natural exponential function. So the number e is an irrational number similar to pi, and this is how people discovered it. They were playing around with this expression, and then they said, well, what happens as n gets larger and larger and larger? So you can experiment and plug in like 100 or 1,000, 10,000, 100,000, so on and so on, and you'll see that this expression approaches this number. So that's what E is. It's approximately 2.71828. And so the importance of this number is that it arises in many applications in the real world. For example, compound interest. If you invest money into an account that is continuously compounded, that means it's compounded like almost every instant, then you're supposed to use this formula. Notice it has the E in there. For growth or decay, this is an equivalent function or formula. It's just that this is used for amount in principle, so it's used in finance, whereas this is used in the sciences. Q can stand for quantity. So you either have a growth or a decay, depending on the interest rate, the rate. If R is greater than 0, positive, that means you have a growth. If R is negative, then you have a decay. So R is what's going to tell you whether it's a growth or a decay. All right, so in 1980, the population of the U.S. was approximately 231 million, and the population has been growing continuously at a rate, so there's a key word, continuously, that tells you that you should use this formula. So we have the initial amount. Initial means starting amount, so that's your Q sub 0 is 231 million. I'm not going to do the 6 zeros. I'm just going to remember that this is in millions, so you don't have to write the 6 zeros. The rate of growth is 1.03. Notice it's positive. Let's convert that to a decimal. If we do, that's going to be 0.0103. Predict the population, N of t, in the year 2020 if this growth trend continues. All right, so they're changing the notation to be N of t instead of Q of t. So I'm going to do the same. I'm going to use N instead of Q. N stands for number. All right, so our function is going to be N of t is going to be the initial amount, e to the r times t. T, we know that t represents the number of years since the beginning of the model to the year that we're looking for. So we need to find the difference between 2020 and 1980. So 2020 minus 1980 is equal to 40. So t is 40. So n of 40 is going to be 231 e to the 0.0103 times 40. And let's see what that gives us. And remember, that's in millions of dollars. To get to the E button, you type second ln, and that's how you get the E button to show up. I'm getting 300. I'm going to round to the nearest whole number. So I'm getting approximately 349 million. It's really 348.77, but I'm rounding to the nearest whole number, so that would be 49. Okay, so that is our final answer. Okay, let's continue. The radioactive iodine isotope 123I used in nuclear imaging decays continuously at a rate of 5.25% per hour. So there's a couple keywords here. Decay, that means our R is negative. And continuously, that tells us that we should use this formula once again, the same formula that we used previously. So let's do that. Q of t equals the initial amount, e to the rt. We know that r is negative 0.0525. I converted this to a decimal by moving the decimal 2 spaces to the left, and I make it negative because it's a decay problem. And all right, it says approximate the percentage remaining of any initial amount after 26.4 hours. So notice they say any initial amount. So whenever they say any, you can choose whatever initial amount you want. For percentages, I recommend using 100 because your final answer will tell you what percent remains after this amount of time. So let's use 100 for the initial amount, and then we have our e to the negative 0.0525, and we have time times 26.4. So type it in exactly the way you see it, and I will do the same, and whatever we get, that is the percentage that remains after this amount of time. So 100 times e to the negative 0.0525 times 26.4, I'm getting 25.007. So approximately 25% remains. So that's why I recommend using 100 as your initial amount, because the answer that you get is the percent that remains. If you would have chose 1 instead of 100, you would have gotten 0.25, and then you have to multiply by 100 to convert it to a percent. But since I started with 100, this already represents the percent, so I didn't have to move the decimal 2 spaces. Now they're asking for half-life. What is a half-life? Well, half-life, what that means is half-life is the amount of time it takes the initial amount to be half the initial amount. So we can start off with 100 again. So let's do that. So Q of t equals 100 e to the negative 0.0525. T is what we're looking for. We're trying to find out how long does it take for the initial amount to become half of that. Well, if the initial amount is 100, then that means we want to try to figure out how much time it takes for 100 milligrams to become 50 milligrams, because 50 is half of 100, and that's what it means to find the half-life. So we need to solve for t. In order to do that, we divide both sides of the equation by 100, and we end up with 1/2 equals e to the negative 0.0525 times t. And then in order to get rid of the e and to bring down the exponent, you have to take the natural log of both sides. So let's take the natural log of both sides of the equation. What happens there is that the exponent, you can move it to the front. So you have natural log of 1/2 equals negative 0.0525t ln of e. But ln of e, that's just 1, because ln is the inverse of e. So these are inverse functions. So ln of e is just 1. It just disappears. And now all we got to do is divide both sides of the equation by negative 0.0525. And that will do it. So on our calculators, type in natural log ln 1/2, close parentheses, divided by negative 0.0525. And I'm getting 13.2 years. It should actually be hours per hour. So whatever the units are for time, those are the units that are going to be the same units you would use for t for half-life. So hours, not years. All right. So that's how you would do half-life. And that's the end of the section.